Thank you, Bryn. Appreciate it. All right, let's get into it. So what I'm going to cover here today is an overview of both, and actually in a very short order, what RBES is requiring for assemblies for above grade walls and some of the changes that are upcoming in the 2024 or 2023 RBES change that Bryn just mentioned for July. But more importantly about the fundamentals behind that and how we can all be evaluating our options for building durable assemblies. So if you have specific questions as we go, please throw them out there. And hopefully what I can provide here today gives some broader context as well. So within the context of that, this is kind of what I'm putting forth as my personal learning objectives on this, on what I'm covering in this content here. So, a lot of this to me at this stage of my work in this field and knowing what I've known at this point and what I've learned and what I've gained from experience and from working with many other excellent people in the building science space is understanding context of material use and the interaction of materials and assemblies and what makes for durable outcomes. So we're gonna get into that, the historical context of materials and what we're working with now, and the effects that the material options that we have access to will manifest into how we put assemblies together. We get into some basic principles about control layers, trying to break down how to put together a building into a matrix of understanding where we do have control to the extent that we can on outcomes and durability for the long term. So we'll talk about control layers and all those interact. And then finally, moisture management, which is the key piece of this, both from the materials choice and interaction context, and then also mechanically what we have options to work with to keep that in check. So just as a grounding principle on all this is, we live in a pretty unique environment here in the Northeast of the oldest housing stock in this country. And this is just a little snapshot from the town center in where I live in Shrewsbury, which is a lovely little mountain town here, nestled between Killington, Peak, and Ludlow. And it's not lost on me how special it is to drive around this state and throughout New England and see these buildings that are, a part of, a lived-in environment that's been around for a few hundred years. And it's great that we still have this fabric of buildings that are a part of that history. So, I'm in being practitioners of this now, we all are here for a reason. We're all building a part of this history by building buildings and retrofitting buildings. So it's important to me to know that what we're doing now will still stand the test of time and be a part of this cultural fabric for the long term. I mean, these are buildings that are 150, 200 years old here that are a part of our core of our town, and hopefully the buildings that we're building fresh, new from the ground up today would be seen the same way and still be there in that same time frame ahead. So in that context as well, where a lot of what we talk about in regard to what the code requires is really landing around new construction and what your options are when it comes to designing and specifying building assemblies and systems for new construction. But the major part of our built environment is existing homes and existing buildings, and we need to keep them vibrant and durable and going for our immediate needs and generations to come. And then we also need to be able to retrofit those buildings as well and not change fundamentally the dynamics of the materials that were used in those buildings when they were built, and integrating and weaving in what we're using for products and equipment and process at this stage too. So a key piece of this, that I'm going to get into here at the start is just material choice and material options that we have to work with. These buildings that have been around for a long time and are a part of our historical context of our built environment, we're built out of local materials and their basic forms. And, you cleared the land, you used the materials of what you had on site to build with. And um, in a lot of ways, the fact that that was how materials were being used allowed for and has given those buildings longevity and an ability to withstand um, changes and seasonal changes and the dynamic of just nature over time. So, we're moving into a changing climate. We are just living in a changing climate. That's just part of our lives here. But, what the materials we put together into our buildings can withstand and how they can manage things over time is the primary context for me in all of this. So, we're moving, we've shifted, and this is a major shift in the resource acquisition side of the equation for construction over the past uh, 75 years, and more so even it's accelerated in the past 25 to 40 years, is where we resource our materials from and what type of materials we're putting together buildings with. We're very rarely, and usually only at the upper echelon of income accessibility, do we have buildings being built with raw timbers anymore. And what we do use is more commodity crop grown lumber. So, there's a lot of benefits for this approach for, commoditizing the products that we're working with and the material that we're working with. It allows for, utilization of the land for a higher yield of material. Um, and it keeps up with the pace of what we're building with, but it does change the dynamic in the material itself. I mean, slow growth lumber versus crop grown lumber is two different beasts that we're gonna talk about in a little bit more detail. And then the labor resource side of it too, as well, has a big factor on the way that our buildings are put together with these local and just site harvested resources. When the land was being cleared a couple hundred years ago, the people who built these homes were more holistic generalists as far as their ability to be able to, harvest the material, shape it into usable components, and then assemble the building in every aspect of detail. And there was a lot of labor effort put into that as well too. And this was a primary means of survival at that stage of development. Where now it's an industry and our labor resources are different. The specialization of the construction industry has really been a significant dynamic change over the past 50 years, where we do not have as many generalists anymore as we do specialists in different categories of equipment and steps and procedures. I mean, you have you're a framer, you have a drywall sub, you have an insulation contractor, you have a HVAC contractor, you have a concrete sub. So I mean, there's many quote unquote specialists that come into play into putting buildings together now too. Ultimately, though, we still need those generalists and the big picture ownership of outcomes in any project to know how all of these components interact together. So that's kind of what I want us to think about today is who's looking at the big picture on these things. What do we have to work with now compared to what we had to work with 100 years ago, 200 years ago? Why we need to be inquisitive and thinking about what the things are that are coming together into a building. We do have specialists, but I think what we've shifted away from though is a lot of those specialty trades really interacting with and digging into each other's pieces of work that they can bring to the table. So that's where I'm going with this. That's my approach I take to putting all the pieces together, and hopefully we'll get some benefit to you all for having going down this road today. And what I'm going to start with is that material choice that we're talking about here. We're talking about using wood in a way that is different than just cutting a tree down on site, keeping it in its raw form, and allowing that material to exist as a part of a structure for the long term. What we go to the lumber yard and purchase and we build our buildings out of now is far and away a lot different than what you would get if you just cut a tree down in your backyard and tried to turn it into a timber to build with. So in the context of that, let's just talk briefly about how wood works and the whole, nature designed trees to suck. That's its elemental purpose here as a part of our biology of our environment is the structure of the wood and the structure of the material here is designed to transport moisture and to move nutrients from the ground up through the tree and up through the leaves. And it's a system that is very efficient in its process and is very specific in its process as well too. And a lot of the dynamic of what allows trees to live, thrive, and grow and be useful as building materials also relates directly back to some of the principles that we talk about in building science. This is a example here in this image of showing that we're talking about pressure differential from the ground to the sky, essentially in a tree, is what allows for that transport of water and nutrients and things from the ground up through the tree to keep it alive. So I'm going to talk a lot about pressure differential today in the concepts of building assemblies and control layers. But, bringing this all back down to the very grassroots, ground roots level, literally, is, this is the structure of what wood is designed to do, is to transport moisture and transport the nutrients from the ground through the cellular structure of the wood itself. So, this is what wood looks like. This is the actual capillary structure of how wood works, and it's highly efficient in this process of moisture transfer, and it's also designed to be capable to manage that level of movement of moisture and liquid through the wood through its lifetime. This is what nature designed it to be. We are at a state though of using wood and these materials as a crop and as a different type of product that we're breaking it down from its original form to make it quote unquote more useful to us in different aspects of engineered lumber and plywood and other material goods that take wood away from its original basic structure that it grows in. So there's a dynamic there to be understanding and taking into account of, about how far away we get from wood in its natural form to what its capacity is going to be in the use as a product within a building to be durable, and what the impacts are for durability of that material over the long term. And this isn't just about breaking the wood down and turning it into other commodity goods. We're talking about sheet goods and engineered structural timbers and things like that, but just the actual physical characteristics of what our lumber looks like that we work with now. Tightly grown together into a forest canopy trees that are old growth, they're slower growing. And so the growth rings that occur annually in that cycle create a denser, more dimensionally stable piece of lumber when you do start to cut that tree down and turn it into dimensional pieces for use for structural purposes. So that higher density structure is more stable over time and will not be as affected by that moisture loading to the dimension of the material. But a lot of, obviously, if you've gone to the lumber yard to try to buy any sort of 2x material, you probably spent more hours of your life than you'd ever want to picking through matchsticks out there in the yard of twisted and cupped and turned lumber. And it's what we work with now. It's what we have access to. But you can just see, this is an example here of the differential between, the dimensional stability of a tightly grown, slowly grown piece of lumber versus these wide growth rings that have a lot more ability to absorb and transport moisture in them that can impact their long-term dimensional stability. And then, taking that utilization of resource to a further stage is when we start to break down the raw form of the material and turn it into some other structural use. OSB and engineered wood products have become just the modern, commodity that we see in just about every structural component of a building at this point, or at least we have access to them for that. It's been, from a material resource standpoint, economically and resource management wise, a huge asset. But at the same time, we're taking trees and essentially turning them into bark mulch and then gluing them back together and relying on the binders and the glue and the industrial process of making this wood into a new form to be functional and to be durable for the long run. So there's a lot of benefit that came out of this transition to product or resource utilization, but at the same time, we haven't quite as much kept up with the consequence side of this. Like, what happens dynamically to these materials over time, and what are those potential vectors for damage that can occur because we're changing so fundamentally the structure of the wood itself. There's no longer that capillary action of moisture management and loading and movement because it's been broken down into this level. It's essentially, like I said, bark mulch put into a functional form. So there's some pretty, precipitative and significant consequences that can come out of that dynamic change in the use of the material. And if we're not factoring in that and accounting for that into the layers involved in an assembly and where we could have potential points of damage immediately and in the long term, then these things can go hidden for years and decades before the evidence of that inability to manage moisture and the changes in the material will show up. And when they do show up, they're oftentimes to this level where it's pretty catastrophic, and we're at a point where the remedy to that is a pretty substantial lift to bring that building back into hopefully a durable state, and then also a healthy state for the occupants as well too. This is the other side of this. We're talking about building durability, going back to the very beginning there. Like, I think we would all want to think that our work as practitioners in this space, as builders and people involved in the built environment, that what we're doing now will be around in a couple hundred years. But that's certainly a factor when you start to see where this damage can go. But also, the indoor air quality and the effect that we are creating little microclimates for keeping humans happy, healthy, and safe with every building that we build. And we don't want to inadvertently pollute that environment because of the dynamic of what can occur through breakdown of materials.
Hey, Steve, we got one question.
Sure.
Go ahead, Bruce.
Hey, Bruce.
I'm not sure if you are unable to unmute yourself to give you permission to talk. Looks like, can you briefly describe what caused the issues in the photos you had, Steve?
We are just unpacking a beautiful package here for you, Bruce, of how to come to this outcome. So I'm going to talk about this in a lot of detail as we go through the rest of the content here today. Ultimately, what this is right here is OSB as a sheathing on these wall assemblies that has been seeing a high amount of liquid vapor, both vapor and liquid water over time, and the inability of that material to dissipate that water and that moisture has accumulated to the point where you just get catastrophic damage. So that's a lot of what I'm talking about here today, is how to prevent and mitigate against this potential outcome in the long run through material choice and just the dynamics, the physics at play that can get to this point if you're not thinking about them.
Thanks, Steve.
All right. And if there's anything that can be done to shift on our end to allow for people to unmute.
If they raise their hand, I can unmute them.
All right. Thank you. But appreciate the question, Bruce, and please, others as you have them come up and throw in the chat, and I'll stop and Bryn will poke me as well. So for context to code, so Vermont RBES is, I'm not doing this content today to be like getting into the dynamics of the how, what, why of RBES, but the one code of the different ICC codes that exist that are set up to kind of define outcomes and process for residential construction that the state of Vermont has decided to implement as a state required condition, a state required code is the energy code. So there's the International Building Code, the International Residential Code are both ICC codes that define the guidelines around just general structural requirements and the big picture around residential construction. But the state of Vermont adopted the Energy Code as the only code pertaining to single-family residential construction in the state of Vermont that is of account for the industry. So what this means is that if you're building what would be defined as a single-family residence, in the context of what the code requires, you are required, as this state statute has defined, to meet the requirements of the Residential Building Energy Standard. And so the Residential Building Energy Standard is updated on a typical 3-year cycle that aligns with the ICC's updates to their model codes of the International Energy Code. And it dictates for anyone building residential buildings or retrofitting them here in Vermont, minimum performance standards for a lot of factors on the building, but really the building envelope, mechanical systems, heating and cooling, the physics side of the equation for residential construction. And the heart of what we get into when we talk about building assemblies in the Residential Energy Code is what is contained in Chapter 4 of the RBES, which is the technical requirements for building assemblies and basically the putting together of the outcomes for residential construction. So this is what I'm going to talk about here in this next section is relating back to those specific requirements in the RBES code of what sections that we're talking about here when we're talking about the requirements for building, wall assemblies, roof assemblies, windows, doors, ventilation requirements, vapor retarders, WRBs, that sort of thing. All of that comes and is defined in Chapter 4 of the Vermont RBES. So the next few slides here are going to be specific to that section. The way that the code is written too is that you need to show technical compliance with the code, meaning that you've built a building or retrofit a building that meets the technical specifications of R values, U values, sizing for equipment, etc., details for air sealing and building envelope air tightness, etc. All of that is the technical compliance side of it, which is the functional details. And then you have to show how you've complied with the code and the reporting side of it through these 3 options that are available. You have a prescriptive approach, quote unquote, which is this packages plus points. We'll talk about that here in a little bit more detail in a moment. There are 2 other options to show compliance that involve using energy modeling software. One is ResCheck, which is a kind of an open source energy modeling tool that's available from the Department of Energy that allows a builder, developer, general contractor, whomever it may be, to enter the building assembly data into that tool and go through a process of iterations of modeling the building essentially to see if what's been designed will be compliant technically with what the code requires. And then the third option is to work with a third party, a HERS rater, who will be doing a more detailed energy modeling of the building and verification as well, which involves coming out, and since there is no code enforcement, there's no code inspection for residential construction here in the state of Vermont. The HERS rating option does give you the benefit of having a third party come out and verify that you're technically compliant to the code and do some performance testing to align with that outcome as well. So these are the three options that are available in the code to show that you've complied technically with what the code requires. And what I'm going to focus on for us to talk about here today is this prescriptive package approach, because anyone who's ever looked at the code for a reference point of like, well, what do I need to build? You know, what's the R value for the walls? What are the U values for the windows need to be? What are the ceilings need to be? What are the foundation insulation need to be? The only evidence of what's technically required for those specific prescriptive values have existed under this option. Those two modeling options of ResCheck and HERS give you flexibility that you can kind of muddy the water a little bit around required R values in different parts of the building. But for the basis of conversation and the basis of, you know, the majority of how people show compliance with the code, and for how the industry interacts, you know, as far as materials, manufacturers, and suppliers on providing products and equipment that meet requirements of code, we're going to look at the packages approach, because I'm going to show you now what those specific assembly values need to be for how the code is written. So if you are looking at the code now, you know, as Bryn mentioned, we have the code update that has been approved and will be implemented as of July 1st of this year. So we have a code change that's come forth, which is what we're basing the conversations around this on today. In the existing code that is in force right now up until July 1st, you have two separate technical tables of options for the code right now, one for prescriptive compliance and then for stretch code. And stretch code comes into play if you have a project or development that is under the guidelines or permitted through Act 250 as well, you need to meet stretch code. Or if you're building in South Burlington, South Burlington has adopted stretch code as their local code requirement, which is more stringent than what base code is. So if you look in the current code right now, there are two packages, two tables listed in the code that define what you need to choose from for prescriptive compliance for base code versus prescriptive compliance for stretch code. And then there's also points that are needed to be obtained based on the size of the building that go beyond those basic requirements and those basic standards for building envelope assemblies that are listed in the base or stretch codes. All that being said is that for 2023, what will be happening in July is this is all being combined into a single table and a single package of points options that you'll see in the code moving forward. So it's kind of consolidating what we have now and putting it into a smaller package and just expanding on the points requirement for stretch code. So if you look in the code right now, under the prescriptive packages option, you'll see this table, which has 5 different packages currently that you can choose from prescriptively. And what is changing is this 5 packages is going away and being consolidated down into essentially a single package. Saying that log homes, if you're building a log homes have always had their own kind of unicorn requirements that are outside of the guidelines of what we're talking about here for Vermont RBES. So there's a ICC standard for log structures, and that is what the RBES references for minimum requirements if you're building a log home. But if you're building any other sort of structure, stick frame, SIPS panel, ICFs, anything like that, you have to fall within one of these other package options. Along with that, there were 2 separate points tables that are in the current code right now, one for base code and one for stretch code. Again, these are points that you need to earn based on the square footage of the conditioned space of the building. So, you know, these packages offered your minimum performance requirements necessary to meet code at a base level. And then depending on the size of the home, you needed to earn points to basically enhance the efficiency of the building beyond with flexibility, with options for how this approach is taken. So what this is consolidating into for 2023 is this is going to be the package you'll see in the code, the table that you see in the code. And you'll see that it's just a standard package, and then log homes. Again, log homes has its own requirements for wall assemblies specifically. So this is what you'll see as a reference point for R values, and now it's also being defined as U value assemblies as well in the code, which is a departure from what has always been the case. So you'll see the above grade wall requirement has a minimum or a maximum U value assembly, and then example wall assemblies of what that could look like. So this modeled 0.044 U valued assembly value for a wall equates to the performance that you'd get with some measure of continuous insulation. So that's the big shift that we're seeing and will be in play. And I'm sorry, my slides, I still have yet to figure this out as to why they jump on me. But if you see the slides jump, that's on my end. The big shift is that the code as of July 1st will require some level of continuous insulation wall above grade wall assemblies. That has not been a mandatory requirement to this point, but that is where we're now going. And so what I'm going to break down today in more detail is, out of these example options. So these are examples of what an above grade wall assembly could look like that would get you to this maximum U value assembly. And rather than have this table be 4 different options that take each of these into account, we're just going to talk about what would be a durable, safe consideration and assembly to take to do a continuous insulation above grade wall package, which is what's required by code now. The other changes of note for 2023 is that if you go back to these prescriptive packages right now, you'll see that we have for a flat ceiling a minimum requirement of R49 for most of these, but package 4 is a common package that we still see a lot of builders use now, which required an R60 for a flat attic and R49 for a slope. These have been consolidated now into 2 different categories of a flat attic and slope. So 2 different, breaking it down into those 2 different assembly types. And essentially, for any sort of flat ceiling, you've got R49 as a minimum R value, and any sort of enclosed slope ceiling at an R44 for a minimum R value. Windows have not changed a lot. We're at a 0.27 U value. That's something that you can still achieve with a double pane window at this point. It does require some specific glazing considerations, low E coating on the right surface to get to that 0.27 U value. That was another thing that was on the agenda for code update, was mandatory triple pane windows, but it did not get to that point. We're still at double pane. But again, to get to a 0.27 U value in a double pane window takes some consideration and specification, and then in other aspects of the building as well. And then just one last other piece of importance here as well is currently up until July 1st, the maximum air leakage rate tested ACH for new construction is 3 ACH 50, and it will now be dropping to 2 ACH 50 for the 2023 RBES. And then finally, this is now, instead of having 2 different points tables in the code, you're going to have 1 single points table that just has 2 columns, and one's referencing your base code requirements for points, and then the other is stretch code requirements for points, depending on the size of the building. So there's a lot of stuff going on here, but there's points requirements for additions, multifamily, and then down here, these last 3 rows are, the reference points for single family new construction from the ground up. So that is the breakdown of what the code looks like. Can I offer any we'll take a second here and chance for any questions.
Hey,
Hey,
Evan,
Evan.
go ahead.
Hey there, can you guys hear me?
Yes.
Yep.
Just curious, what's the state planning as far as enforcement on that U value on fenestration? Because, we test for actual, metric values on ACH 50s, things like that, but we're not doing some massive envelope test to see what the overall U value is on fenestration. It's kind of more just like a guideline, or, they tell you what you should be doing and what you have to do, but again, no enforcement. Are there plans to actually get boots on the ground checking this thing?
No.
Okay.
No, and I mean that's been the perennial question and issue raised around these requirements with the code for years. Is it's the way that the code is written. It's really it's on the builder to be the one complying technically, reporting and technically documenting compliance, and being accountable for the outcome. So it does, the way that this is written, rather than enforcement through code officials or some regulatory process, it basically puts the building owner, the client, giving them options to hold the builder accountable for not meeting technically what the code calls for.
Okay.
So, when it comes to U values as well, it's a weighted value for all fenestration throughout the building too. So you technically could have some exposures or portions of the building that exceed that 0.27, but if that's balanced out by other units that are below that, then that's considered compliant as well. That's where more specifically the res check and the HERS rating option to show compliance allow for more flexibility with stuff like that. So I mean,
right.
Like with HERS, it's based in numerical, score of the overall energy, performance of the building. So, conceivably in that approach, you could have a building that has higher performing wall assemblies and other components of the building, and yet windows with a U value that are 0.29 average or 0.30.
Right.
That
Well,
would
they
be
look at things like
compliant.
solar heat gain coefficient that Vermont decided to get rid or no longer value in the code. So
Right.
there's just different metrics. It kind of does seem that, that's, while I fully agree with trying to get everyone on the straight and narrow and doing things right, quote unquote, there just does seem to be kind of a little bit of discrepancy with what is important in certain areas of the build, just through either HERS or through the prescriptive method. It's all good stuff, but it just seems a little bit all over the place.
Well, that's one thing I didn't throw into the slides here at the outset of this is our role in this as well too, is that we Efficiency Vermont's role in this is to train, educate, support compliance and just technical knowledge around the code. The Department of Public Service is the entity that is the one responsible for where the code is going for technical requirements, policy alignment, statute itself.
Right.
So there's been a lot of feedback, and a lot of back and forth on these factors. That is one of the bigger constraints of prescriptive compliance with the code as an option, is that there isn't that level of flexibility. It's just prescriptively thrown out there that like it has to be this, and it doesn't take into account those other factors of solar heat gain or exposure or other factors in the building if you're going to use the prescriptive approach to show compliance.
Right. All right. Thank you.
Sure. Appreciate the question.
Thanks, Evan. We do have a couple more questions, Steve.
Okay.
The first is the 2024 RBES code on the public service website shows a 0.30 U value for fenestration. Has that changed again?
It depends on which version you might be looking at. So, this is what I've got in here is pulled. Actually, you know what? I think you might be right on that, Jeff, because there's been so many changes. There's a chance that could be accurate, that got bumped to that 0.30. We'll follow up as a, follow up from the call here this morning, but that was being batted back and forth. But the table that I'm pulling from for this was what was in the version of the code that was put forth to the committee that approves, the update for statute. So, but we'll follow up on that to confirm if that's been shifted or not, or if that's even an option at this point.
And the next question from Jason is, what will the code be for 2024 window codes with the new federal Energy Star of 0.22U on Windows?
And it doesn't have an effect on this. I mean, Energy Star is its own labeling program and voluntary standard that a builder can choose to meet, that's administered by the Department of Energy. So there's been at times conflation and overlap between what the Vermont Energy Code required and what the Energy Star standards for performance look like. But Energy Star is a voluntary program, and it is not aligned with what the state of Vermont's policy is in regard to what the code would look like. So, that the values that are aligned with Energy Star new construction codes is its own thing, separate from what we're talking about here.
Great question, though. Thanks, Jason.
Yep.
That's it for now. Steve, thanks.
Okay. Thank you. All right. Well, thanks everyone. I appreciate the questions and keep them up as we get through some more content here. So now we're going to get out and geek out on, the details of, we've got the technical side of this out of the way. So let's talk about how do we actually specify and put these things together. So we're creating little microclimates with every building that we built, and looking at what our options are, what our ability is to have control over that microclimate. There's components of the building envelope that we put together, and specific dynamics at play and specific expectations that we have from each of those building components and those layers that will keep those frail little human occupants comfortable and happy and healthy and safe inside structure, without the structure falling apart around them. So we can really break it down into some specific layers, and we're talking about controlling thermal losses of heat and energy, air movement, and what air can move through building assemblies as you have leaky assemblies, which then trickles down more specifically into moisture transport, which is specific back to that image that we showed earlier. The question you had about how did that happen, we're going to get into that in a little bit more detail. And then finally, we're at the point, that mechanical ventilation is hugely important for the benefit of the occupants of the building, as well as just building durability itself and the building assemblies. What the big dynamic between the 200, 150-year-old structures that we have in our built environment versus what we're building now is, again, because those buildings were built out of material in its raw form, those types of structures can handle a tremendous amount of moisture loading seasonally and not fall apart, because the wood is basically in its original form. It's designed to move and to manage that flow and that ebb and flow of moisture, liquid, through the material. And if you're not significantly altering that dynamic within the building assemblies, those materials will continue to do that for decades and centuries. And what we're talking about now, though, is everything I said at the beginning. We've changed that material approach, and we're not building with that material anymore. So now we have to be very careful about considerations of what those materials can do, what their capacities are. And a key thing that we really, our building science has legitimized through vigorous testing and analysis and research over the past 30, 40 years, however long we want to call it, what it is, quantifiable aspects of what works and what doesn't work within buildings. And so there's no question anymore at this point about the need for having airtight building assemblies, because the more leakage you have through assemblies, the more moisture transport occurs and the more vectors for damage occur and the worse indoor air quality we get. So, that's a fundamental here of airtightness, which is a big key of what we'll talk about, but then managing the different aspects of the building assembly or the building indoor environment as a result of building airtight assemblies. So when you break down what any sort of building assembly is going to look like, we have 4 distinct control layers. The bulk water control, which is essentially our siding, the cladding that we're using as our primary first line of defense, essentially between what nature will do to us and to our buildings from the outside, trying to keep that water away from the structure behind it. The air barrier is the pressure boundary between inside and outside. And this is the key gateway of air tightness between indoors and outdoors. That's an assembly that needs to be detailed robustly and for the long term, and is the primary mechanism for creating that pressure differential between inside and outside. Thermal control is whatever warm fuzzy stuff we want to throw into an assembly to try to slow the transfer of heat energy, the conductive loss of heat energy. We cannot stop the flow of heat energy from warm to cold. That is physics at play, and this is what we have the ability to influence, but we can't stop it. We can control it to a certain extent. So there's a lot of options, obviously, with what our insulation types are to control that conductive transfer. And then finally, vapor control. Humans are big off-gassers from living in their homes and their buildings. There's a lot of moisture to manage and the use and function of our buildings, and we need to know what options we have to keep that in check at its primary sources, and how to mitigate moisture from building up to a point where it becomes too much to manage by the rest of the assemblies and layers that we're talking about behind it. And then what options do we have to protect the different layers that we just talked about here from moisture penetration, from moisture getting into them, and if moisture does get into them, how can that be managed when that happens? Because again, we can't stop these things. We can only control them and then give them options to be mitigated once they occur. So, this is just a section kind of detail of looking at where those different layers actually play out. So we have our exterior cladding surface, the primary control layer for bulk moisture. In this assembly, we have a couple different things going on, which is evidence of what we're talking about for that requirement for continuous insulation now in the code, where we have a WRB as another layer of moisture control, keeping bulk water from the exterior of the building from reaching the vulnerable sheathing materials behind it. And then ideally also that WRB allows for any moisture that would have accumulated within the wall assembly behind it to pass through and dry to the outside. The air barrier is in green here, and that air barrier again is the primary pressure boundary between inside and outside, almost uniformly in the types of construction that we see every day. Our sheathing layer of the building is our air barrier, but we'll talk about that in some more detail. And then the thermal control layer here in this example, we have cavity insulation and a continuous insulation layer on the outside of the sheathing. And then finally, our vapor control layer. That vapor control layer is what's seeing the indoor environment and is our material option to mitigate vapor transmission into the wall assemblies and the layers behind it. So these are the passive approaches that we have to controlling these things. We'll talk about the mechanical side of it, of managing indoor air quality and moisture and humidity itself. But when we talk about putting building assemblies together, these are passive approaches that we have. You specify the material, you take into account the dynamics of what that material can handle. But then once you build it, it's kind of left to the world to decide if it's going to be there for 10 years, 20 years, 200 years. So material choice and the interaction of all these different materials together is what creates durability. So you can't isolate any of these individually on their own. They all have to work together. So you have to have all of these components accounted for and hopefully identified uh, specifically in drawings and within your subs as to who's responsible for what. That's another big piece of this too, is like, well, who's responsible for the outcome that each of these layers is going to perform at. And again, that goes back to, there's different specialty trades that are involved in each of these layers, literally, like, siding contractor, framing contractor who's going to be putting up your sheathing, insulation contractor who's going to be doing the insulation work, but who's looking at the big picture? That has to be some generalist within the construction team that can be, holding the subs accountable and also just knowing that nothing's been missed in that putting together the assembly. So any quick questions on that? And then we'll start to get into some pressure dynamics. And then probably take a break here in 5-10 minutes.
Nothing at the moment, Steve. Thanks so much.
All right, sweet. So pressure dynamics in buildings. We're talking about physics at play here. And there are some fundamentals to that are never going to be, we're not ever going to affect. So we just have to learn and know how to manage for them. So pressure dynamics exist within buildings due to a variety of different factors, but conceptually, if you want to think about, how a building performs, is that, the bigger the temperature difference between inside and outside is a primary driver of pressure differential. So the bigger the temperature differential between inside and outside, the more the pressure difference, and the more small pieces of the puzzle that are not where potential leaks may be can be more impactful, because you think about a balloon and you poke a hole in it, moving that air out in a short order through a small space. So again, pressure dynamics and pressure differentials within buildings has a few different vectors of how that occurs. Temperature being one of them, as I just discussed. The bigger the temperature differential between inside and outside, the bigger the pressure difference. Wind moving on the surfaces of a building creates significant pressure differentials on different orientations of the building as a result of that. So if you have a 20-30 mile an hour wind blowing on the east side of the building, you'll have high pressure on that side and then low pressure on the other side. So creating suction essentially because of that exposure to the wind pressures that the building is seeing. And then finally, the other major dynamic is mechanical equipment that's physically exhausting air from within the building to the outside. Thankfully, for new construction, this is less of a factor than it has ever been before. What we do have a lot of buildings, though, experiencing in our built environment, especially in the Northeast, is, we had buildings that were built before there were central heating and cooling systems put into them. And then, those buildings now have furnaces and boilers in them and chimneys and ways of needing to exhaust combustion gases from equipment. And pressure dynamics within buildings can change the ability of that draft from working the way that it should work, just naturally. And then also mechanically, you can throw things off balance. By changing pressure differentials, by putting in exhaust fans where there wasn't before, and atmospherically vented equipment or fireplaces that are relying on a certain amount of air from within the building for that draft and those combustion gases to get outside. So this is a big factor when it comes into retrofit work of existing buildings, is to really understanding the dynamics at play for the potential of depressurization for existing mechanical equipment. Again, thankfully, where we're at now with modern mechanical equipment and codes is that everything now at this point is pretty much closed combustion. So the air that's required for combustion and ventilation of those gases is coming directly from the outside, and it's going to be less influenced by pressure changes within the building that could create unsafe conditions. But coming back to it, these are the main, fundamentals that impact pressure within a building assembly. So we're going to now jump into the air barrier assembly, that we're talking about pressure differential and the air barrier as the control layers of those 4 control layers is the primary control layer that we have to create a pressure differential between inside and outside of the building and create the primary layer of control for keeping indoor air and outdoor air from mixing through building assemblies. So this has a huge impact on comfort, energy use overall for the building, and building durability. And maybe this would be a good moment. We're about an hour in to just take a moment, a couple, 3-4 minutes, let everybody grab a cup of coffee, think about any questions, and then we'll jump back into it. That sound good, Bryn?
Yep, that sounds good, Steve.
Okay. All right. I'm going to go do that myself, grab a little more coffee, and I'll be back in a couple minutes.
Great, thanks so much. And for the folks that are sticking around, I'm going to just put another link or two into the chat. If you are not already a member of the Efficiency Excellence Network, we would love to have you join our membership. There's no cost to be a member, and we provide a number of trainings similar to this at no cost or low cost. As an EAN member, you get a discount to attend our Better Building by Design conference, appreciation events throughout the year, special member only access to financing for projects, as well as some appreciation events that we hold throughout the year. So certainly welcome anybody that has interest. You can, if you haven't already considered it, please, fill out an interest form. We also, one of the greatest values that we hear from our members is having their company information cross-promoted on our Find a Pro tool on our website. So you can visit that to see what some of the service listings are, what the trade groups are, who else in your area is listed for some similar services that you might be providing. But want to give you a chance to learn a little bit more about that and peruse it. And if you reach out to us, we'll follow up with more information. But like Steve said, let's give you a few minutes break and we'll be back in a minute or so. Thanks so much. Hey,
All right.
Steve. I did want to jump in before we head off onto this next session. I was thinking that one additional resource that folks may have interest in or may know of folks that have interest in, we do still have incentives available for flood recovery for businesses as well as residents. There's a link in there for some additional information for all of our flood recovery programs. So if you have any questions about that, please don't hesitate to reach out. We want to help, and we know that there are still a lot of people that are putting their homes and businesses back together from the flooding that's happened this past year. So I'll hand it off to you, Steve. Thanks so much.
All right. Yeah, thank you. Appreciate you bringing that to point here. It's something I've been involved with myself for the past few months. So yeah, stay in touch if we can be of any help on that front. Yeah, so air barriers, there's continuity, compatibility, and durability that come into play. And this really goes for any of the control layers that we're talking about. But stitching together a bunch of disparate materials is what constitutes oftentimes the assemblies that we're talking about here. And so understanding, how to make those transitions occur between different components within the building, and then making sure that they're durable over time is really what matters. So, accounting for these as you can before you start putting the structure together into what your options are for materials, what your material choices are, being able to delineate these on construction drawings, if and when possible, is always ideal. And then once you start to put them into practice, understanding what your options are for controlling those outcomes. And again, it's not one prescriptive approach that needs to be taken with a specific type of material or a specific approach taken to get a really good air barrier assembly. It's oftentimes a combination, again, of a variety of different things, but it's understanding the details of where those that continuity needs to occur, what your material options are to make those sorts of transitions. So again, you're looking at different aspects of the construction being oftentimes installed by different trades and different subs within the context of putting a whole project together, but being able to have someone or some line of communication between the crews to identify those points of needed transition and or continuity, that you don't miss anything along the way. And there's a lot of great products on the market now to allow for this as well that are specific to this purpose. You can see some of them in here in this, these pictures right now of different tapes and materials and membranes and sheathings. But it can be very basic as well, for what we've become accustomed to for materials and process as well to create a good air barrier. These are just some examples of what you'd see typically in an open attic assembly, where the ceiling drywall is essentially your air barrier. It's providing a lot of different roles actually in an open attic flat of air barrier, vapor control, and holding back the thermal insulation as well. But just going through and spray foaming closed cell foam over all of the penetrations and top plates of the wall, stitching together what otherwise would be a bunch of broken up sections of drywall around an overall attic plane, with a lot of pathways for air leakage. The idea of spray foaming all of those stitches this all together so you have a monolithic layer of drywall with no leakage pathways, no penetrations through it. And then on top of this, you blow in as much insulation as you want and or need to meet code and to meet the project objectives. So the key here is that it doesn't have to be complicated. It doesn't have to be specific as far as material options or choice goes. It just needs to be thorough. It needs to be continuous, and it needs to be durable. So that's where we get into material choice, and the fact that we're breaking down materials from what their capacity is in its natural form to how we need to use them and what we need them to do within the context of durability in a structure. So perm rating is the terminology that you've probably already heard a lot of, and is going to be and continue to be a major part of the conversation around material choice moving forward. Is the permeability rating of a material is how efficient it is and what its capacity is for vapor transport through the material. So 1 grain of water vapor per hour per square foot per inch of pressure is the definition of what defines a perm. The big point takeaway from this is the higher the number, the higher the perm rating, the more ability that material has to transport moisture vapor through it during a given period of time. So higher vapor transport, greater ability to absorb and release and transport moisture during a heating season is essentially what we're looking at it to do in our environment here. So this matters pretty elementally to me at this point, you know, for our material options that we have for assembling wall assemblies specifically, and then roof assemblies as well. So we're creating and generating a lot of moisture vapor within the building during, you know, the use of the building during the heating season. Managing that primarily with mechanical ventilation is the key defense mechanism. But as I've been saying throughout this, is that we can't stop these things from happening. We can't stop thermal conductive heat loss. We can't stop moisture vapor transport. We can slow it and we can control it to a certain extent. But we have to accept the fact that there's going to be a certain percentage and volume of moisture vapor that makes it into building assemblies during a heating season. That's when things accumulate because of that pressure differential, because of the dynamics of drying capacity, because of temperature as well. So this is the time of year where we see moisture loading really happening within building assemblies. Because the mechanisms for drying do not exist easily and freely at this time of year. So you're going to see loading of moisture within walls and roofs and assemblies this time of year. And then what happens when that loading occurs? First of all, you want to minimize it as much as possible. But then secondly, when it does happen, you know, what is the capacity of the materials involved to allow for that to not damage the material and then to transport outward and dry, you know, over time. So there's considerations to be played into primarily the sheathing that we use, the weather-resistant barrier as a membrane, either integrated into the sheathing and or on its own as a layer of fabric that you'd put on the outside, that the, you know, structure of that material and the capacity of that material or how it's even engineered to work has an influence on how readily it's going to transport moisture vapor in a drying capacity. So these are things I'm going to talk about here in more detail, and we'll look at some specific examples. But the key, you know, one of the key takeaways, and I'm sure you've all heard this before, is the vapor barrier sandwich. We see a lot of these issues with buildings that were built in the 70s through 90s of there was less building science understood at this point, less of a understanding of these pressure dynamics and moisture loading and permeability of materials that we do have now. And the products that were available on the market kind of, you know, became uniformly used without understanding the implications of what might happen over the long term if we're not accounting for that drying capacity to occur. So as I say here at the end, you know, just about any material assembly combination can work as long as you understand the characteristics of the permeability of those materials and you allow some mechanism for vapor transport to occur and for drying to occur. So breaking it down specifically into sheathing material options, plywood, CDX as a sheathing material is wood more in its raw form. It's veneers of raw logs that are glued together. And as a commodity, you know, OSB has kind of dominated the market for sheet goods comparatively to plywood for a long time because of cost. Essentially, it's cheaper to make OSB than it is plywood. But we're talking about material, as I said here, you know, you can see the layers in this plywood here. It's veneered peels of lumber of logs. So it's wood and it's more of its raw form. And as a consequence of that, plywood CDX has a much better or has a high capacity for moisture loading over time and moisture management without delaminating, without shifting, without, you know, rotting is the key, kind of the key thing. So there's a consideration to be played when you talk about your options for sheathing the building of plywood versus OSB. So again, alternatively, OSB, you know, is that concept of what I brought up earlier. If you're taking trees, you're turning them into bulk bark mulch, and then compressing them into a usable form. And there's a lot of glues, there's a lot of binders, there's a lot of other components that make that work, that create the material in the form that we use it as. And as a consequence of that, there's a very limited capacity for the wood component of this to be able to transport moisture vapor. So it's a low perm material. And so there's a consideration to be played in choosing CDX, plywood versus OSB in a wall assembly, depending on the other materials that you're going to put in and around it and behind it. Along with that, we have Advantech and Zip sheathing, which are OSB products, and the Zip system is uniformly used, and I'm sure you've all used it. And now we have Zip R sheathing and different iterations of it. The big thing Zip brought to the market, Huber brought to the market with the Zip system, is that it's a sheathing product that integrates the WRB, the weather resistant barrier, into that product in one pass around the building. So a huge impact of the Zip product on the market is that because of the fact that you need to tape all of the field joints of the panels to create that uniform weather resistant barrier, you also got really good air tightness out of the sheathing layer of the building. Because prior to that, you'd slap up the OSB or whatever you were sheathing the house with, and you didn't tape anything, and nobody paid attention to the gaps that existed between the different panels of sheathing you put on the building. And we had some really, really leaky building assemblies as a result of that. So this is a product that allows for a bit of that to, both of those processes to occur in one shot, but at the same time, we're still talking about a product that has very little capacity for vapor transport. So there's not a lot of drying capacity through Zip sheathing to the exterior. That green coating that they put on it as the WRB actually has a pretty high perm rating, but the substrate that it's bonded to, which is the OSB, does not. So this is a low permeability sheathing material. Doesn't mean it's bad, doesn't mean there's a reason you shouldn't use it. And the Advantech is actually even less permeable. But what that means then is that as you look at the different control layers behind that of insulation, material options, and vapor control, you need to be making sure that assembly has drying capacity to the inside, because this type of material is not going to give you a lot of options for outward drying. And as I mentioned, another key component of, I'm sorry, Evan, I think I saw your hand up. Did you have a question?
Yeah, can you hear me?
Yep.
So I just wanted to bring something up just because I thought you were going to dive into more of the Zip system stuff. But something I see all the time, that people, they tape their joints and everything, but they're not taping the rough opening sheathing back to the studs at the ROs, and they're not taping the Zip system at the base where it meets the pour. So there's, it's kind of like, it's great, you can tape your Zip system all you want, but unless you're taping the, every single key joint, you're only as strong as your weakest man.
Yep. Thank you. That's a good point. I mean, that's a part of hopefully what we'll iterate towards further in this, is that, the details really do matter. The key thing that I will say though, and hopefully what I get to with this is that with the Zip sheathing, the big shift fundamentally in process that occurred with Zip sheathing being commonly used is that people started taping their sheathing, which was never done before. I mean, when I came up learning how to put buildings together, I didn't tape sheathing as a common practice. So that became more uniform into the practice of addressing your sheathing layer of the building. So that gets you a lot of the way there as far as that pressure boundary and air barrier goes, but it doesn't account for all the details. So getting back to that though, I think one of the big key things for me is the fact that tape has a lot more capacity for durability than the other things that we would have used in the past to seal up these sorts of joints. And what you were just mentioning, Evan, like around window rough openings and door rough openings, the transitions between framing to concrete and other stages of the building, is that, caulking versus tape like caulk is meant to bridge a gap between two disparate materials that are going to move over time and stretch when those materials move. But the way that everyone always installs caulking is you put a bead of it into a joint and then you smooge it in there with your finger and then you bond the whole thing on all three sides. And that's what you see here is this pathway for failure, is that you no longer have this stretching capacity where if you did it right would allow for the joint to move and that caulk to stretch over time. You actually end up tearing the caulking because those materials don't, the caulk material doesn't have a pathway to stretch. It's bonded all the way around. Whereas the tapes, the zip sheathing tape and other pressure sensitive acrylic tapes, that's kind of the specific here, is pressure sensitive acrylic tapes have a really high bonding capacity and they stick tenaciously and they won't fail over time. They have different capacities for strength over time. I mean, they can resist different dynamics of the material movement to what they're bonded to. So it's the bond that counts, the fact that they're actually going to bond to the material and that they're going to stay flexible over time, more resiliently than some of the other things that we used to use back in the day to handle these things. And so this is where those details count to what you're bringing up, Evan, I think is, you can have a specific layer that you control, but it's the details then as you transition into different parts of the building that really matter. And I am a curator of tapes, I will say at this point. So I'm a true believer here on this front. And this is just a small sampling of some of my like typical collection of this is the type of stuff that I've used for different reasons. So there's different types of tape for different applications, and there's different dynamics at play for the types of tape that you have access to and why you would choose it one versus the other. So it really comes down to, being curious about what you have access to for materials and trying to dig into the details a little bit more. So, this is a type of vapor permeable, pressure sensitive acrylic tape that's airtight, but it does allow for moisture vapor to move through it. And the concept being that the substrate that this tape is going to go onto would probably be CDX, and the permeability rating of this tape is similar to what the CDX would be. So, meaning like if you sheathe your building with CDX because you want to have high vapor permeability for the sheathing layer and good drying potential to the outside, the last thing you'd want to use is a type of tape that doesn't have any drying potential to the outside because it's plastic essentially. So, then we get into some of these other pressure sensitive acrylic sheathing tapes. This is the 3M 8067 weather sealing tape, which I used a lot of this. I think it's a pretty universally flexible, literally and figuratively type tape that can do a lot of different things and be used for a lot of different applications. It's very stretchy, tenaciously bonding. You can use it for a lot of details that in the past you probably would have tried to caulk and it wouldn't have worked very well. But there's a big dynamic difference between this material right here, and you can even just see it in the image, right? This has this like, looks like a honeycomb, structure to it. And this is just essentially a membrane piece of plastic. So this is going to have moisture vapor transport capacity. This is not. Doesn't mean one's better than the other, but you just need to consider like why you would choose one versus the other for a different application. These are now getting into butyl tapes where you're looking at specific applications for shedding of water around window and door rough openings, and potentially why you'd choose this type of adhesive over any of these other three. And then you get even into more detail about, specific tapes that are engineered for specific purposes. These are some of the other vapor permeable tapes that are designed around window installations and sealing around specific joints where you need a bend in the tape to make that transition occur well. So, and then, gaskets, adhesive gaskets that would bridge that gap. I think, Evan, to what you were just saying, between your sheathing and your foundation. Somewhere if you overhung your exterior sheathing past the sill plate down to the foundation, which is pretty common, you could use a gasket like this as a point to seal that gap or tape. So the point I'm making here is to just be curious about what your options are and to dig into it a bit and consider the compatibility for outcome as to why you choose one tape versus another for the type of material that you're bonding it to. And also make sure that the materials that you're looking at here are compatible. If your tape doesn't stick to the substrate, stop using it and find a different option. Here's a couple examples of that. So, foil-faced phenolic foam that a foil-faced tape was technically supposed to bond to and adhere to, and obviously it was not. You can see it's not bonding here. It's not bonding anywhere. But unfortunately, in this example, a lot of it was used before the crew were made aware that they should probably stop wasting their time putting something that isn't working on the building and just try to find a different approach. There's another example as well too. These are SIPS panels, so structurally insulated foam panels. It's EPS behind that OSB there. And the builder in this example, chose to make the effort of taping the seams of the SIPS panels to seal them up, make them airtight, quote unquote. But that's a staple right there. So the tape was actually stapled to the OSB because it wasn't sticking. So that's another example of someone just kind of blindly going through the day, wasting materials and time and outcome. They were rolling out tape onto OSB that wasn't sticking, and then they were hitting it with a tack stapler to keep it attached so it didn't fall off the wall. So if this isn't going to work, just stop and identify it early on that it's not working and choose a different choice. So this is what ended up happening in this example. That foil face tape obviously was not doing the job. So for a couple different exposures of these walls, you had to go back and take that tape off behind the strapping and then put a tape that did actually stick onto the insulation to take care of what should have been done the first go around. So the other point to take around this too is just protecting the materials and giving them the best chance they can get as far as keeping bulk water away in the first place. Ignore the Tyvek in this example. This is not here as a final layer of protection on the building. This was a temporary layer there to get through a winter before siding could be put on. But the example to look at here is the fact that we've got 1x3 furring over the continuous insulation as that primary drainage plane, deeper overhangs whenever possible to just allow for any runoff from the roof above to get away from the walls behind it. We're not talking about needing a lot of separation between cladding and exterior surfaces to allow for vapor diffusion to occur. This is the Benjamin Obudoki house. Oh geez, I'm going to forget the name of it. Yeah, I'm forgetting what it's called at the top of my head right now. But these little rubber nubs.
Hydro gap.
Thank you, hydro gap. Thank you. But these are very tiny little nubs that are bonded to the face of that hydro gap. But that is enough to create just a capillary break. We don't need a physical break as much with the 1x3 strapping as you see here, as just an ability for moisture that's coming through the assembly behind it to just diffuse outward. So you don't have to make it, robust, quote unquote, physically to create that pathway for vapor transport from, the wall assembly to the outside to dry. Even just 3/8 strapping here ripped behind the siding is enough of a disconnect between the assembly behind it to allow for that drying to occur. And then the same with your WRB options. You have different products and materials that are available on the market that are engineered to provide a layer of bulk water protection from, the water or rain driven and environmental driven wetting from the outside, but then also allow for that vapor transport to occur from within the assembly that it's attached to. So these are just 3 different examples of 3 different commonly used products that are WRBs on the market. You can just structurally see that they're quite different in how they're put together. So researching the perm rating of the material, understanding how it's meant to work for that vapor transport and how that's going to interact with the materials behind it is really what I'm getting at here, as far as just digging into the details a little bit more. Any questions?
Not seeing anything,
All
Steve.
right. So thermal control, now we're getting into insulation choice. And it can be a variety of different things. I don't think that there's any need to be, specific that one insulation type is better than another. It really comes down to the interaction of that material with the other material choices that are in the assembly around it. So cellulose, spray foam, wood fiber, fiberglass. I mean, we see all of these products in use, and they're all viable products from a thermal control standpoint. But what we do want to mitigate against is this potential of that damage potentially occurring to the structure in and around it, because we haven't accounted for control of vapor transport, of drying capacity, of mechanical ventilation. And within the context of material choice as well, you have, this is just a visual example of 4 different types of continuous insulation. That being required now coming forth in July. And we'll talk about now some of the options for doing continuous insulation assemblies. But here's 4 different examples of 4 different insulation types that you could specify for use as continuous insulation. You have rock wool, mineral wool, rigid board, extruded polystyrene, phenolic foam, and polyiso. So 4 commonly available continuous board stock insulations. Breaking this down even further, now here's 3 different options of essentially the same insulation type. So these are phenolic foam boards, but with 3 different types of facing on them. So the facing on the material also has an impact on vapor transport, its capacity within the assembly as well. So I can't get into all of the details of why one versus the other through, the context of our time we have here today. But what I'm hopefully getting at for you all to dig into is to just be curious about what those options are. There's so many options out there now. Just being curious about what the different dynamics of each component of that material are capable of doing and how that interacts with the other materials you're putting together into an assembly. So, the fiberglass facing on this has a different impact on the drying potential and moisture transport of that insulation versus this foil-faced polyiso, the typical foil-faced polyiso that you see here, and then this, which is a perforated aluminum facing on the foam board as well. So I'm just going to go into some common continuous insulation wall assemblies now that are options for showing compliance with the Vermont RBES, but also options that we all need to be considering for how do we specify now continuous insulation wall assemblies, what makes sense from a cost standpoint, what makes sense from a moisture management standpoint. So it's a variety of different approaches that can be taken to this to get to the same outcome. Double stud walls are one of those common approaches where you're just framing 2 different wall assemblies and creating a depth and cavity between those 2 wall assemblies to allow for dense packed cellulose insulation to be installed. The depth of that cavity and the performance of that cavity is really essentially dictated by what your final R value outcome would be that you're aiming for. The deeper the wall, the higher the R value. I'm going to show some examples here in a minute about how to detail these sorts of assemblies to make sure that they do remain durable and that dense pack installation is maintained over time. So this is one of the more common approaches to doing continuous insulation wall assemblies. Exterior rigid insulation. So I just showed that slide of an example of different types of continuous rigid exterior insulation that can be used for any sort of wall assembly. Here's an example of the mineral wool board option. So the key takeaway when it comes to doing exterior rigid insulation over a cavity filled wall assembly is there is a minimum ratio you're going to want to achieve in the R value of the continuous insulation to what is in the cavity, and that's 50%. So if you have R23 of fiberglass or rock wool or cellulose in a 2x6 framed wall assembly, and then you're going to put continuous insulation on the outside of that wall over the sheathing, as is shown here, you want a minimum of half of that cavity R value in the thickness of the insulation you're going to put on it. And that thickness is going to differ depending on the material choice that you have. And then the ability for that wall to dry, if it does see moisture, is going to be affected by which material choice you come up with for the continuous insulation as well. But that ratio of 50% of cavity R value is pretty critical when we're talking about any sort of wall assembly, and this translates to roof assemblies too, where you're putting some sort of fibrous insulation into that wall or rafter assembly that can load moisture. So if we're talking about spray foam here in the cavity, it's a different ball game, closed cell spray foam, but any sort of insulation material in that cavity that can that is vapor permeable. So that's fiberglass, that's rock wool, that's cellulose, that's open cell foam. It's a lot of different things. You need to have 50% of that value of R value in the continuous insulation outboard of that sheathing. As an alternative to this, and what we're seeing more of in use these days, is nail-based panels of continuous insulation sheathing. So the zip R sheathing, where you have an exterior structural sheathing layer that's bonded to a thickness of insulation behind it. And the intent here being that you can still sheathe the wall structurally as you normally would, and you get a continuous layer of insulation behind that. So there's differences in thicknesses and R values of these panels available, and then other considerations to take into that for what you put into the cavity behind it. These would be considered assemblies that are going to have very limited, if not zero, drying potential to the outside. So it doesn't really matter what the WRB is or the capacity of that green coating of the zip sheathing. That wall assembly, if there's moisture that gets into the rock wool or cellulose or whatever's put into the 2x6 cavity, that moisture vapor is going to need a pathway to dry into the building because it's not going to get to the outside. And so that's why there's this recommendation here of a smart vapor retarder on the interior. We'll talk about that here in more detail in a moment. SIPS panels, structural insulated panels, you've got a thickness of typically EPS foam that's laminated to 2 layers of OSB on the inside and the outside, and the thickness of the panel defines the R value. Again, these are assemblies that are going to be pretty airtight if they're put together right, with limited drying potential to the outside. So really managing indoor relative humidity and moisture levels with mechanical ventilation is crucial in these types of construction. And mitigating moisture transport into the assembly from the inside is pretty critical in these assemblies as well. Finally, a little bit more of the esoteric. We don't see a lot of these so much, but everybody's tried something at least once, right? So the Arctic truss or TGI truss wall would be an approach where you frame structurally a 2x wall assembly as your bearing load structural wall, and then hang on the outside of that TGIs or engineered truss joists to create your insulation cavity. And you can make that as thick and as deep as you want it. I, this was something that was being played around with and tried 10 years ago or so now, and we really don't see much of it happening anymore. But just goes to show you there's a variety of different ways you can get after these things to the outcome. So what I thought would be helpful here in context as we talk about continuous insulation wall assemblies is I wanted to kind of dive into it a little bit deeper with the zip-R panels and considerations for material choice and details on that. But it seemed like as I dug into it, that might be its own training to attempt. But we're going to see more of that as common practice. We're seeing a lot of that done now. So there's some specific considerations when choosing to go down that road. But another common approach is dense packed cellulose double stud wall assemblies or rafter roof assemblies as well. So these are very safe and durable and carbon friendly building assemblies, and a lot of examples of these types of assemblies that are out there and resilient. But again, it does come back to detail, not only for the specification and the detailing of the control layers of air barrier, vapor control, bulk water control, all of that, but also how the insulation material is installed itself in the assembly. And so dense packed cellulose assemblies are really, their long-term durability and resiliency is dependent on the fact that they're going to remain at that level of density over time. So when we start to get into thicker assemblies beyond a 2x4 or 2x6 for dense packed cellulose, there's actually some really crucial details that need to be accounted for and put into practice so that that density can hold up over time. Because what you don't want to see happen is that material sag or the density not be there and gaps and voids open up in the material that can make the entire assembly vulnerable to moisture over time. Similarly, as if spray foam could, not be installed against a dry substrate or under, certain conditions where the foam could shrink back from the substrate that it was applied to as well. You don't want those sorts of occurrences happening, and you don't want those gaps opening up. That creates some very vulnerable pockets within the assembly that can fail over time. But getting back to cellulose specifically is, calibration of the equipment being used and the installer who's using that equipment really has a huge impact on long-term outcome and durability. So, really understanding about how to calibrate the equipment and ensuring that you're getting proper density when using the equipment, checking in on that on a regular basis. So I'm putting these sorts of points out here just as a potential things to be talking to installation subs about when considering hiring them to do this type of work on a project. Is what is their approach? Do they have any evidence of calibrating their equipment? Do they do bag checks as they're going through the process? Are they installing the netting and the insul web appropriately based on the design of the cavity that they're being asked to insulate? So, there's factors involved in this. I mean, there's bag counts that you can look at based on density. So you should be able to look at data from the installer of how many bags and volume of material are needed based on the anticipated density to be achieved for the cavity that's being installed in. The basic parameters of just equipment setup of the insulation equipment, the volume versus air pressure, and actually calibrating at the end result with the hoses to make sure that the volume and density of the material coming out on the end is meeting the target of what's intended for the durability of the assembly. So just here's some examples of that methodology in practice. insul web being installed to contain the cellulose insulation, proper stapling techniques even of where to staple that insul web so that when the material is installed in the cavity, it's not blowing out past the face of the framing and you're getting the actual density that you need because this is nice and tight and taut. When you have big depth cavities and huge expanses, this really comes into play with like this right here for a deep rafter and or a double stud wall, is you need to start to isolate sections of those cavities in order to get density. You can't just take a wall that's 30 feet long by 8 foot tall, that's 12 inches deep and double stud and fill that whole thing with cellulose insulation, expect to get density. You have to isolate cavities in order to make that happen. So these are just some examples of how this process can and should play out for the long-term durability of the assembly. Proper technique for filling the cavity, for going back in and touching it back up to make sure that you have proper density, how to evaluate density once you have it into the cavity as well too. Making sure you can both visually see and physically feel that you've achieved the intended density for each of those cavities as well. So again, coming back to who's responsible for the overall outcome for the project, on general terms, as the general contractor or someone who's responsible for big picture outcomes, these are just some things to be putting into your head about what to talk to your subs about, what to be looking at for detail, and just hopefully, making sure are being uniformly deployed throughout the process that you put the building together. Any questions before I get in the last section here about vapor control? Not seeing anything in the chat at the moment.
No, you're doing great. Thanks so much, Steve.
Okay. So that brings us to our last passive control layer that we have the ability to define, which is vapor control. So as I said, humans off gas a lot, and we generate a lot of moisture within our buildings, and we need to control that at a point source, but then we also need to mitigate what is going to be in that indoor environment and makes its way into these assemblies due to pressure and temperature differential. So a big factor too, when we talk about new construction, is that there's a huge amount of moisture within a building for the first couple heating seasons. I mean, you think about a foundation that's poured and you build a house right on top of it, and we build into the winter, and you're capturing so much embodied water in those assemblies, just as part of the practice of normal construction. That loading needs to be accounted for, especially in those first few years, to really just bring it down to a manageable baseline, and then to manage the long-term indoor humidity for the occupants and for the assemblies. So high humidity left unchecked is going to lead to damage to building envelope assemblies, mold, mildew growth, indoor air quality issues for the occupants. So breaking down of other materials. So there's a lot of, this is the crux of it all, which we don't necessarily track as well, I think, in what we often talk about for code and building assemblies, is the whole idea of managing indoor air quality and moisture is kind of left out there in the ether for somebody else to take care of. And we'll talk about the mechanical ventilation side of it, but that's the key point of management. But passively, we need to know, like, how do we keep vapor out of assemblies? So, we have a lot of ways that it's going to be generated within the building, and a lot of potential for loading if we're not managing those point sources to begin with. The major mechanism that we're talking about here when it comes to indoor generation of humidity and moisture is water vapor. We're not talking about liquid water necessarily coming from inside the building into assemblies. That's very rare unless you have leaking building components. Or capillarity, which is where you're going to be wicking water from a wet spot to a drier spot where you're moving water from wet to dry. Really what we're talking about is the amount of moisture vapor in the air within the building, and then the pathways that air can make it into the building assemblies. That's why it's crucial to have a really good air barrier to create a very good pressure boundary between inside and outside as your major defense mechanism. And then secondly, managing on the inside face of the building what the actual, assemblies of the walls and the roof and the ceiling are going to see to the occupant side, to the inside of the building, making those assemblies as airtight as possible as well, and using materials that are going to retard vapor flow through them as much as possible. This is a classic example from Building Science Corp about the concepts potentially behind this of diffusion, about how much moisture vapor can move through materials over a heating season. So as an example here, if you have a 4x8 sheet of drywall, untreated, no paint on it, no finishes, and that sheet of drywall is over an insulated 2x6 wall assembly with the conditions of an indoor air temperature of 70 degrees at 40% relative humidity throughout a heating season, which is pretty typical, common, which we don't want to get above 40% relative humidity in general. Just vapor diffusion through that sheet of material, that 32 square feet, will transport a third quart of water into the insulation and the assembly behind it through diffusion during the heating season.
Steve,
But
a question.
Yep.
And you might get to this with the ZIP-R system. How critical is the interior smart vapor barrier? We've seen Jeff has seen a lot of construction without the interior SVB.
Mm-hmm. I think it's crucial that you have that, and you have some mechanism that allows for interior drying. I kind of see that interior vapor control layer as a insurance policy on the assembly behind it. And we'll talk about that in some more detail here now, Jeff. It's about details again, because you can conceptually do it and get good vapor retarding through drywall itself without using a smart vapor retarder. But it really comes down to how well it's detailed. So thanks for that question. It leads into the last of the content here for us to cover, and it's a crucial piece of the equation for sure. And as a consequence of that, this is the example that we're kind of getting at, is that if you're not paying attention to the details of that interior vapor control layer, whether it's a membrane, a smart vapor retarder, or if you're relying on drywall to be that defense mechanism, the vapor control layer is minimizing the amount of direct air leakage pathways through that control layer into the assembly behind it. So a 1-inch square hole in that sheet of drywall will transport up to 30 quarts of water into that assembly during the heating season. So that whole idea, like I showed with the balloon, pressure differential, you start poking holes into it, the amount of moisture vapor transport that can occur through these small gaps may seem inconsequential in their own distinct, consideration, but when you start to magnify them across the scale of an entire wall assembly or roof assembly or an entire building, is where these things get magnified, and you can get to the point where you get so much transport of moisture into an assembly, you start to get to that point of damage, which is in that early slide that was asked about as well, is how does this damage happen? Why are we looking at that picture of that rotted OSB? This is how, this is why. This is what can happen with it. So we have to keep these things in check. The main defense mechanism here is having good mechanical ventilation, so you don't have high humidity to begin with. And then beyond that, you do want to keep any sort of moisture vapor within the building from getting into assemblies and coming in contact with cold surfaces. So these are some of the strategies that we have access to control passively with these assemblies over time. And this is the dynamic that you can see in these assemblies. If you could, break them apart during a heating season, this is what caused that damage to the OSB in that picture I showed at the beginning, was an accumulation over many months worth of time and over many heating seasons of warm indoor air with high humidity leaking, getting through the drywall, getting through the interior finish of a wall assembly, and coming into contact with cold surfaces on the sheathing of that wall, the exterior sheathing, that were below the dew point, and moisture vapor basically in the wintertime turning into frost and accumulating on the backside of that sheathing, and then just sitting there and saturating the materials behind it, saturating the fiberglass, the cellulose, the OSB, the CDX. If it were CDX, probably, wouldn't show that level of damage as I did with the OSB, but the OSB just saturates and it doesn't dry. It does just not have a mechanism to allow for that to happen. And this picture right here, this is not spray foam that's bonding fiberglass to OSB. This is actually a layer of frost, which is a cutout of a section of a wall assembly where this dynamic had been occurring. So this is interior vapor transport that is accumulated to that thickness of frost against the cold OSB in the middle of a heating season. So this is the physical dynamic of what can occur when we're not managing those control layers well. Here we go, back to those same examples again. This is the damage vectors that occur and what it can look like. So our options to keep this from happening are to A, keep that moisture out, manage indoor relative humidity with ventilation, mechanical ventilation. If the water and moisture vapor does and will get into those assemblies, you need to give it a clear pathway that it can dry outward to. And what we're talking about, the zip sheathing there and the zip bar, or any sort of low permeability exterior surfaces or sheathing on a building, you need good drying potential back inside to allow for that to occur. So, and also just, try to keep any surface that could see moisture above the dew point. And that's the reason for that rationale behind that 50% ratio of continuous insulation thickness, an R value ratio between continuous insulation and cavity insulation. That whole ratio, methodology there is to keep the sheathing above the dew point throughout the heating season so that won't occur. Vapor control options, we're talking about vapor retarders. We're not stopping vapor. We have different categories and classifications of vapor retarder from class 1 to class 3 and vapor open. So the higher the perm rating, the more vapor permeable the material is. Smart vapor retarders have a kind of unique dynamic of where when they see higher humidity levels on the interior facing side during the heating season, they will prevent, or I'm sorry, the opposite of that, prevent that moisture transport through the material. So it'll act as a vapor retarder. And depending on the product, it can be very effective, almost a class 1 vapor retarder during the heating season. But when those dynamics and those humidity levels changes, that material will open up and allow for diffusion and drying to the interior of the building. So this is that kind of capillary dynamic where the material itself is behaving kind of like what wood would be doing in its own natural form. That will allow for that drying potential to occur in these assemblies that have limited drying potential to the outside during the summer months. So we want to create assemblies that are going to be durable to that moisture loading throughout the heating season, because they will see that moisture loading. We want to minimize it as much as possible, but then know that if they are going to see moisture, that it's not going to reach a critical point where damage can occur. But then once the dynamic changes, that building assembly can dry out. And so it's this ebb and flow. And you can see this through monitoring that's done of building assemblies as well, where you put probes into an assembly and look at it over a few heating seasons. You can see this curve of moisture loading and then diffusion and drying as you get into the summer, and dropping to a minimum level by July or August, and then that curve going back up again as you get deep into the heating season. So that's a road that can be traveled and can be maintained. What you don't want to see is it peak and then really never bottom out as far as that drying goes, season over season, because then that just accumulates with time. So these are some of the intelligent, smart vapor retarders that are available in our market that we do see into play. The Intello is probably the most common one, and the one that I've seen as being most effective in my mind, and that I've used a lot. You can see the range of the permeability of the products based on the manufacturer's testing. So Intello has a 0.17 perm rating when we're talking about the exposure it's going to see during the heating season and its ability to retard vapor flow through that material into the cavity behind it. So it has one of the lowest perm ratings for that to serve as a vapor retarder. And then it also has a pretty high perm rating on the other side of the equation for that potential drying potential during the summer months outside of the heating season. So more to look at into there. Details is really what matters. You know, the same idea around detailing your interior vapor control layer should be taken into account as you would with your exterior air barrier details, making sure that you have products and materials on site throughout the process of construction that allow for the ease of this to be installed. You know, here's a interior partition wall that lands between two trusses, and it's in this circumstance the builder had the Intello vapor retarder on hand so that they could install that before that partition was built, which makes it a lot easier to detail than it would have been to try to patch that all into place after the fact. So again, big picture thinking, you got to work with all your subs, and each has their own specialty, but thinking about these levels of details as you go through the construction process to stitch it all together. Again, it doesn't need to be one product only, one versus the other. Here's an example of Intello being used as a vapor retarder with dense packed cellulose in the cavity behind it. That transitions into a limited rafter depth roof assembly, low slope roof that has closed cell foam installed, both as our thermal control and then also as the vapor control. So we're relying on the R value and the density of the foam here for R value, but also as that vapor retardant control layer. So no moisture will get to that from that to the roof deck. Another example here of just those framing and interior construction details. You have a cavity here, dense packed cellulose cavity where you have vapor control of that Intello installed over the dense packed cellulose, but then you have a whole corner of windows. And each of these, the gaps that would occur between your header and your king studs and your jacks are pathways for moisture vapor to get through those, stacking of lumber, which could get to the sheathing behind it, which could create pinch points for moisture transport and moisture accumulation. So, in this example, what we did here was using a airtight and vapor permeable tape that would allow for, keeping moisture vapor and air from getting into those, but still allow for drying potential back into the room as well. So it's stitching together the details that matters.
Steve, we're just over time, so if you want to
wrap it up here. Yep.
Thanks.
So again, last couple details of just thinking about these transitions and building components, sealing around windows into rough openings and sealing the gap between the window rough opening and the framing is critical. But then also, again, keeping moisture vapor transport from occurring into that gap as well. So this is just an example of sealing that gap between the window unit and the rough opening, but then putting a vapor retarding tape there that would keep moisture vapor from getting through what would otherwise just be open cell foam, and getting to a vulnerable point of the vinyl installation flange of the window on the outside. So yeah, we are at time. The last few slides were just about mechanical ventilation. We can skip through that, but everything that we've talked about to this point is what we have access to control passively through building assembly choice. We do need to have mechanical ventilation in these buildings as well. That's another code change for 2023 or for July as well, is a requirement for balanced mechanical ventilation. So that'll be another session we'll do here coming up is getting into more detail about this, but we have to have adequate control of indoor air quality, primarily humidity levels, and using balanced ventilation versus exhaust only is just what we need out of our buildings at this point, regardless of what code is actually dictating or requiring. So we'll talk more about this in another session and get into this in more detail. So thank you for taking the time to be with us here this morning. Hopefully this was helpful in some way, shape, or form, and feel free to keep in touch with questions, or I can stick around here for a few minutes here too for any other questions that might come up.